Hello. In this video we're going to be going over Learning Objective 4 from Chapter 20, Lecture 20. We're going to be looking at the standard cell potential, or E cell, also known as the electromotive force, calculating it out, and looking at how we actually derived these values, or how someone derived these values. Okay, so our cell potential, or electromotive force, is the force that pushes electrons from the anode towards the cathode. We call this an electric potential. Or a electromotive force. Or EMF. Last one is our E cell. It's another way of looking at it, which is the cell potential. So all of these are interchangeable, but the unit for this electromotive force, or cell potential, or electric potential, is the volt, where 1 volt is equal to 1 joule divided by 1 coulomb. And we can rewrite this as a coulomb is equal to a joule volt. Okay, so C is coulomb, and is a uppercase C. And then volt is also an uppercase V. So it basically tells us the amount of work the cell can perform. So, we use what are called standard reduction potentials when determining our cell potential. So our cell potential itself is calculated as the reduction potential of our cathode minus the reduction potential of our anode. Or we could write it as the reduction potential of our cathode plus the oxidation potential of our anode. Remembering that, or noting that the reduction potential of our anode would be equal to the negative oxidation potential of our anode. So if you're looking at the reduction, the negative will give you, the negative value of that would give you the oxidation. Each of these reduction potentials were determined using or comparing it to hydrogen gas. So a standard reduction potential is the reduction of hydrogen gas, or compared to reduction gas. The reduction of H plus to hydrogen gas. So specifically, the following equation, 2H plus, reacting with 2 electrons, produces H2 gas. So this reduction is set equal to 0, and then everything, all the reduction potentials are compared to this reduction potential. So if we have a value of a reduction potential, that is greater than 0, it means it is easier to reduce than H+. If we have a reduction potential that is less than 0, it is harder to reduce than H+. Okay. Our standard hydrogen electrode, or She, is used in order to determine reduction potentials. So they take and they compare the reduction of any species or oxidation of any species versus hydrogen. So on the left, we see hydrogen gas going to H plus 2 electrons. So this is an oxidation process. So the opposite of the other one. And then this is a reduction process. So because hydrogen is getting oxidized in this case, we would say that the copper 2 plus is easier to reduce than hydrogen. So our reduction potential of Cu2 plus is going to be greater than 0. If we take and compare another thing, such as zinc, we see that H plus is being reduced in this case, and zinc in this case is being oxidized. Because we have the reduction of H plus in this case, we would say that our zinc is harder to reduce than H plus, so our reduction potential of zinc 2 plus is less than 0. So we compare either one of these, either the production, this electrode will be the same either way. You're going to bubble in hydrogen gas, and either you're going to be going from hydrogen gas to H plus, or you're going to be going from H plus to hydrogen gas. One of the two. And then that will determine whether you have a reduction potential higher or lower than that 0 point. So let's look at both of those examples that I just showed. So in the first example, we were looking at copper. So we have H2 gas going to 2H plus and 2 electrons, right? And here, this is, in this case, an oxidation, and it will be equal to 0 volts. Right? The copper is going from copper 2 plus to copper solid, and here this is being reduced. And want to determine what that reduction potential is by going back and looking at the volts produced here. So the voltmeter in this case read 0.34 volts. So that means that our cell potential is 0.34 volts. So if we combine these two equations, Cu2 plus H2 going to Cu solid plus 2H plus, the overall cell potential here is equal to 0.34 volts. So you can use that information to actually determine what the reduction potential of copper 2 plus is, remembering that our E naught of our cell is equal to E naught of the reduction of the cathode plus the E naught oxidation of the anode. So we have 0.34 volts is equal to our cathode, which is what we're trying to solve for, plus 0 volts, the oxidation. So our reduction potential of our cathode is equal to 0.34 volts. So this right here is 0.34 volts. Okay. We can do the same thing with the zinc. We see here when the zinc is reacting, we're going from zinc solid to zinc 2+, so it's being oxidized. So in this case, our hydrogen electrode is acting as the reductant. So it's going to be, in this case, it will be our cathode. So we have 2H plus AQ plus 2 electrons going to H2 gas. And again, we know that that value is 0, but now it's the reduction value. And at our anode, we have our zinc solid going to zinc 2 plus 2 electrons. And this is our oxidation. Again, we look back, we see our voltmeter had a voltage of 0.76 volts. So our cell is 0.76 volts. So when we combine these two equations, 2H plus zinc solid goes to zinc 2 plus H2 gas. And now we set up our E cell equal to a reduction of our cathode plus oxidation of our anode. So it's 0.76 is equal to 0 volts plus our oxidation at our anode. So our oxidation potential for our zinc is equal to 0.76 volts, which means that our reduction potential for zinc is equal to negative 0.76 volts. So we see that zinc itself is harder to reduce, which is why I say negative value. Those reduction potentials are tabulated here, where we have our 0 point as our She electrode, right? And then anything that is easier to reduce than hydrogen gas or hydrogen ions is above that point. Anything that is easier to oxidize would be below that point. Okay, so let's try this out with the following two problems. We want to determine our cell potential for these two electrochemical cells. So we've got zinc solid reacting with copper 2 plus to produce zinc 2 plus and copper solid. Let's break it down into our two reactions. Zinc solid goes to zinc 2 plus and copper 2 plus goes to copper solid. We need to add in electrons to balance charge, and we see that our top one is going to be an oxidation, our bottom one is going to be reduction. So if we look on our table, zinc is right here. The reduction potential of zinc is negative 0.76. But if I want to solve for the oxidation, it'd be the negative of that reduction potential. And then the next one that is a reduction potential right here, the 0.34. And it's positive, so our E cell is going to be those two values added together. Which gives us a value of 1.10 volts. Okay, let's try the next one. We're going from copper solid to copper 2+, and from silver plus to silver solid. Top one we add 2 electrons, bottom one we add 1 electron, but we need to multiply this whole thing by 2. Wait till we do that. I'm just going to go ahead and put it across. This is 2 electrons, 2 and 2. That will not affect our reduction or oxidation potentials, just as a note. And I forgot to combine these real quick. 1 second. When we combine these, we get Cu solid plus 2Ag plus going to copper 2+ plus 2Ag solid. So the top one is an oxidation. So we'll take the negative of our reduction. So it's negative 0.34 volts. And then the bottom's our reduction. So we look at our table. Ag plus 0.80 volts. This balancing does not affect our reduction potentials. Combine these two, we get an E cell equal to 0.46. That's everything for this lecture and this video. I will see you guys later.